Good afternoon, all, and thanks for attending this afternoon's webinar. I'm Craig Edwards, the Business Development and Technical Director from William Johnson's, and I've got great pleasure to introduce you to Johannes Müller from TEADIT, who will talk about hydrogen sealing and some of the process and application details this afternoon. Over to you, Johannes. And just before I do, one final thing, if we can leave any questions just at the end of Johannes's presentation, and at that point, I'm sure he'll be very glad to answer them for you. Thank you.
Okay, thank you, Craig, for the kind introduction, and welcome to today's webinar. Also from my side, I'm Johannes from TEADIT, and I'm the Energy Transition Manager, so I'm responsible for the coordination of the hydrogen projects on our end here. And today I would like to talk a little bit more about the complexities of sealing in the new energy area. And the main context of my presentation, of course, is hydrogen and fugitive emissions. So today I would like to talk about what and why we want to use hydrogen. Of course, why leaks are concerning in this kind of market or application. And in the end, I would like to present how we better can control the leaks and what are our ideas and solution for the hydrogen sealing. Of course, everyone is talking about the energy transition. So in the past, coming from fossil fuels and the energy conversion via combustion, we had emissions, and these emissions we can now skip totally from our environment, so to say, using hydrogen. So focusing the hydrogen production is the key in this kind of business here, as we can store hydrogen, use it for energy, for the energy sector, in easily converting it via fuel cells in a emission-free point of view. There are different ways of production of hydrogen, so that's why mainly the method of the production really matters. Of course, hydrogen can be produced from coal, for example, but this production causes CO2 emission, and this is not required anymore. So that's why normally, or the future plan is to use low emission production of hydrogen via solar energy, wind energy, and water energy usage. As you for sure also know, there are different types of hydrogen separated into a color spectrum, so to say. What we really see here is that the minimal amount of electricity is used to produce hydrogen. Most comes from still fossil fuels, where we can produce turquoise, blue, gray, or black hydrogen, depending on the production method, from methane gasification, from natural gas, for example, or from coal. We as TEADIT are more looking into the electricity-based hydrogen production, as we see the sealing components as a main component in the hydrogen production, as they can be used as a sealing solution, of course, in the stacks or in the electrolyzers. As mentioned briefly, most of the hydrogen isn't produced from electricity, unfortunately. So in this chart, you can see that most of the hydrogen is produced from natural gas. Here it is light gray columns also without carbon capture and utilization and storage. Most of the hydrogen right now is produced in China. This can also be seen in this map here. So the square orange dots are early stage projects on globally, and what we can see is that we have a lot of running systems globally, but when going into the operational part, you can see here in Japan and in China that there are a lot of electrolyzers already installed for hydrogen production. Europe is a little bit more crowded, so we know that there are several projects running, for example, in Spain, in Germany, in Scandinavia, the UK. So Europe is in a very, very good position to be competitive in the hydrogen business here. To better understanding the market, we should also look a little bit more into where hydrogen is currently used for. What we see here, beginning from 2019, is that most of the hydrogen is used in industry here. We have some refining from oil, but the new ideas of using hydrogen will come from 2030 on. So what do I mean when I talk about industry applications? So hydrogen is very important for the production of ammonia, also for the agriculture sector, producing fertilizers, and in minor applications also for textiles, for example. The second biggest part in industry is the methanol production here, also resulting in a formaldehyde production and other chemical solvents or acids like acetic acid here. As mentioned also, we can use hydrogen for oil refining, hydrocracking, or hydrotreatment here. When we want to talk about the new applications in the future for reaching our net zero emissions, we can for sure talk about synthetic fuel production. Also, steel making is a very big topic here. In Germany, we have, for example, ThyssenKrupp. They already started the production of a new plant that totally will transform, or they want to use hydrogen for the production of their whole steel production here. Yeah, but why are gasket manufacturers focusing hydrogen and have to keep an eye on it? So hydrogen is very challenging to seal, as it's a very small molecule size and highly permeable molecule. It's invisible, colorless, and does not smell, which makes it very hard to detect. When looking into the usage and the energy density, so to say, hydrogen is 2.5 times higher than methane, which is also written here in this chart on the right side. Unfortunately, hydrogen carries 1/3 of the energy of natural gas here. So to maintain the same energy, higher pressures are required. Safety always has to be focused when using sealings for hydrogen applications. we really have to take care that we do not allow hydrogen to mix with air, because then it can explode very quickly. Here in this chart on the left-hand side, you can see that hydrogen in blue has a lower minimum ignition energy compared to other common fuels like natural gas, propane, or gasoline vapor. Here, one very nice example that the hydrogen flame is invisible, which can cause some risks here. Also, environmentally, we should take an eye on that, as hydrogen has a high global warming potential. So the oxygen of hydrogen in our atmosphere produces water vapor, leading to stratospheric cooling. The H+ ions, so atomic hydrogen, can also lead to the formation of ozone, which is a greenhouse gas, and hydrogen reacts faster with OH- in the atmosphere, which is also essential for breaking down methane. So hydrogen is kind of using the OH- before it can crack the methane. So we really should ensure that we do not emit hydrogen gas from pipelines or during hydrogen production. When looking into a little bit more into standards, what can be tested or what testing are performed can be separated into cat gaskets and packings in different norms and standards. So for the US market, everything is written down in the ASME and then the API standard. For Europe, we have the EN 13555 measurements and the ISO 15848 measurements, where it's written that you have to test with helium. Of course, TEADIT, for example, did some testing of their PTFE materials also with hydrogen. We are able to test it in-house here on our MTech machines, seeing that the performance at higher surface pressures of the gaskets is producing better leakage curves when compared to helium. In the North American market, by standard, everything is tested with methane. Just that both gases are mentioned here. When looking into the kinetic diameter and compare it to each other, we have here the three gases. On the left-hand side, we have a helium atom, which is the smallest molecule here. In the middle, we have our hydrogen, and on the right side, methane. So when looking on the chemical structure of the gasket, it's quite obvious that methane should be easiest to seal because it's the biggest molecule here, and helium is the hardest to seal. Bringing this into a comparison, leakage-wise, or looking into the leakage curves, on the left-hand side, we have a leakage curve of our expanded PTFE product with helium gas, and on the right side, we have the same material with hydrogen gas tested under 40 bars at room temperature. what we can see here and circled in red, as I mentioned, when going to higher surface pressures, the ePTFE material seals the hydrogen one leakage class better than compared to helium here, which of course is quite good because this underlines that our material certifies for hydrogen usage, not only for ambient temperature, but also at elevated temperature. When going into the hydrogen production, which is our main part, we putting our R&D in, because without the hydrogen production, we won't have any pipelines or hydrogen for the piping systems to transport to the end customers. So what we have here are 3 different technologies: alkaline electrolysis, proton exchange membrane electrolysis, and solid oxide electrolysis with with PTFE material. We have to focus alkaline and PEM electrolysis, as the solid oxide operates at very high or elevated temperatures, and PTFE is melting starting from 280 degrees Celsius here. When comparing these 2 technologies, we have some slight differences. For alkaline, we have always an electrolyte, a liquid electrolyte, which is most of the time KOH. In some cases, it also can be sodium hydroxide. It is very good for a large-scale production. It's very cost-effective as you can use cheaper materials for the electrodes, the end plates, and the cell frames. When going to PEM, it's getting a little bit more expensive, as you need a solid membrane with these platinum group metals, which are rare metals, making it more expensive. But you have a higher hydrogen purity. What we see when working together with companies from the industry is that typically every manufacturer is using their unique gasket design, meaning that you really have to go into a detailed exchange with the customer to produce or to manufacture the best fitting gasket solution for their application. What we see is that in PEM electrolyzers, you need thinner material. Going to alkaline applications, you need thicker gasket materials. Of course, we also need to focus chemical compatibility with the fluids, not even in the hydrogen production, but also when transporting hydrogen or trying to remove impurities. Not a big problem, but a huge discussion when talking about sealings for hydrogen applications. Sometimes can be the creep relaxation of the PTFE materials, as when seeing temperature, the material tends to expand. But here we are well prepared, also changing the properties of the material a little bit. What we did in-house here is that we try to better understand our materials and how they perform in installations. So we equipped our laboratory with 2 prototype stacks, so to say, looking a little bit more into the performance and the gasket creep, so to say, when applying it in a real system. On the left-hand side, you can see a small table stack, so to say, where you can test 100 gaskets at the same time. Here we equip the stack with load cells and also with stress measuring gaskets to really understand better how the material behaves when you use a stacked system, so to say. The bottom picture, actually we have also a alkaline stack in our company here in Austria, where we also performed a lot of testing of our material, seeing that all material is compatible with the usage in hydrogen applications, except the glass-filled materials. So we knew from literature research that the KOH is dissolving glass fibers or glass spheres, and as we also have a glass-filled material in our portfolio, we of course tested it and wanted to understand how it behaves when it gets in contact with KOH. And what you can see here is a darkening of the material in a 35% KOH, and that's why we do not recommend glass-filled material for hydrogen applications with KOH. For the transportation of hydrogen in pipelines or in trucks or tanks, this should be not an issue, as no KOH is used here, of course. TEADIT as a company has a densely instrumented laboratory. With our R&D team and application engineers, we try to collect as many data from the market as possible to start the exchange with the end customer, offering a compatible and a best sealing solution here. So what we do now are customized sealing solutions for the hydrogen application. So we put a lot of effort in contacting partners, looking for cooperations to, on the one hand, better understand what their needs are, and on the other hand, helping them, supporting them with our know-how and knowledge in hydrogen application here. So this is what I always try to underline. We really need to exchange on this topic here to really use the right material for every application, because it's so complex. When thinking a little bit more about the value chain, electrolysis stands in the middle of everything, so to say. We need at first the hydrogen, which should be produced to use it for other sectors here. On the right-hand side, we are a little bit more focusing power stations and, so to say, the green hydrogen production. And on the left side, it goes a little bit more into changing the production from refineries away from coal or oil, so to say, using hydrogen here. Why I'm showing this chart here is almost every gasket material can find application in the bridge building system. If it's for flange connections, if it's for the component in stacks, it really depends on how you handle the problems and how you try to find solutions for that. As mentioned during my presentation, here I would like to overview the products a little bit that we see in the hydrogen application. PTFE products work very, very good when they are in contact with hydrogen, as they are chemical compatible to almost everything. Also, yeah, if it's pure PTFE, also to KOH. On the left-hand side, you can see our restructured PTFE material, which is filled with glass, barium sulfate, or silica, and in the middle you can see the expanded PTFE, which is very good working whenever you use flange connections or hydrogen production, transportation tanks, as well as a component in the stacks. As my position says, we want to focus even more the energy transition, supporting the global revolution of producing more hydrogen and the carbon neutrality until 2050. We are well equipped with our laboratories, with our factories, to do the testing, to improve, to increase volumes, all to handle the needs of the market here. And now I'm at the end of my presentation, so whenever there are questions, I would like to answer them.
Thanks very much for your presentation, Johannes. Very interesting, very enjoyable, very insightful. I don't know if there are any questions from anybody within the audience this afternoon. If there are, then please use the message facility to type them through. We'll give you a couple of minutes to have a think about it, but if not, then potentially we could look to wind up just after that. Thank you. You must have covered absolutely every aspect there is to cover, Johannes. There don't seem to be any forthcoming questions. So all that really remains for us to do is to thank you very much for your time this afternoon. Thanks to the Pipeline Industries Guild, and certainly a big thank you to Johannes Müller from TEADIT for his insightful presentation and talk on hydrogen sealing. Thanks very much.